This morning. I do have the ability also for you to come on and answer questions too. So as we go, please feel free to unmute your microphone, ask a question, then put it back on mute so we don't hear all your background noise afterwards. Uh, let's see. I'm going to mute some of these out already. Let's see. Looks like they're mostly muted. All right. Well, good morning, and I'm sorry we have to meet like this, but it's nice to stay home, I hope. Today we want to do sort of the natural extension of what we were doing with conic sections. We're going to do quadric surfaces. See if you can see this, I hope.
You're going to need to move the camera up a bit.
Yeah, thought I had the top of the blackboard when I turned this off.
That's perfect right there, actually.
Okay, let's try that then. Can you see it all right?
Yes, sir, once you move your head.
Okay.
There you go. That works. That's great. Thank you. Working good.
Okay. Tell me if there's too much glare, and there's a light coming off of here. So today we'll talk about quadric surfaces and also cylinders. These are the most common surfaces in three space that you run into are these here. Why would we see these more than others? I want to put a preamble here to the whole thing and say one of the reasons they come up so much is that they're real useful. They come up in lots of things. You see them in some of those, uh, for instance, planetary models. If you take, I've worked a little bit with models of different planets and even the Earth. If you take, for instance, the Earth is pretty close to the sphere, right? But it's spinning, and so it's not quite a sphere. And if you want to compute a real accurate latitude and longitude, your GPS does not use a spherical Earth. It uses something that has ellipsoidal cross sections. That's why we studied ellipses first. You take this ellipse, and then you revolve it around its axis, and it is pretty much a circular cross section horizontally. Where this is north through the North Pole. But width-wise, it's a little oblong to get accurate GPS coordinates and accurate things for satellites. I used to work at Vandenberg Air Force Base as a safety analyst many years ago, and we used an ellipsoidal Earth model. This is the WGS, whatever the current year is. 1984 was the year they sort of really standardized it, but there's some more recent ones since then, much more recent. But this one's still used a lot. World Geodetic System. Using an ellipse if they revolve, and this is then called an ellipsoid. We'll get to the general equations, but I just wanted to motivate this. This stuff always goes down better if you first see some use for it and go, wow, that's neat. I did a paper many years ago on Phobos, the satellite for Mars, and I was just, as a graduate student, reproducing some of the work somebody else did for my class. And they use an ellipsoidal model even for Phobos, even though it's not all that round like the Earth. But this is a pretty common model. And it's also used in gravity models and so forth, and lots of other places. But all of these quadric surfaces, such as this, have this neat property that not only are they really useful like that, but their cross sections are conic sections, which are studied a lot. Furthermore, they all come out of this equation like this: ax squared plus bxy plus cy squared plus dy d plus e squared plus fxz plus dx plus hy plus iz plus j equals 0. That's a mouthful. But it's actually not hard to remember. Why would that not be hard to remember? This is just one example. It's called an ellipsoid. It's a three-dimensional surface whose cross sections are ellipses, and it's an example of a quadric surface. We'll mention shortly. All the quadric surfaces come out of this. This looks just like your equation for conic sections, except in three variables, right? It's a general polynomial of second degree in x, y, and z, three variables. And after a plane, a linear function, ax plus by plus cz plus or equals d, this is the next highest polynomial equation equals 0 generates the quadratic surfaces. And so they're pretty simple. They have lots of applications, and their cross sections are conic sections, so they're well studied, and we understand their properties like asymptotes and semi-major axis and all those things that we did last time. So this is the motivation for them. This is always, just like we did with conic sections, either one, a quadric surface that we're going to mention here, a degenerate case, or no solution. Doesn't that sound familiar, like conic sections? It's just one more variable, a surface in three-dimensional space instead of a curve in two-dimensional space that gave us conic sections. So this is just adding one more dimension to what we do with conic sections. All right, so that's the introduction. If only I didn't write on this with permanent ink. There are 6 of them, like there are 4 conic sections, and then there are a bunch of degenerate cases. Let me see if I can put this up and try and share the screen here. You can just Google quadric surface or quadric surface Wikipedia, and you'll find the following information. Let's see if I can get it back here. What's coming up? Is it still not working? Looks like it's not. I'm trying to share the screen here. There we go. Maybe if I get it. Just didn't push it long enough. There we go. Okay, so here are the quadric surfaces off of Wikipedia. Can you see the quadric surfaces?
Yes, sir.
Okay. The first one is the ellipsoid I mentioned. It has this standard equation, just like the conic sections have standard equations. This looks like the equation of the ellipse if you get rid of this last term here. X squared over a squared plus y squared over b squared equals 1, recall, is the equation for the ellipse. So you add one more similar term and you get the ellipsoid. And so these are actually really easy to pick up once you understand the conic sections. I like to do the hyperboloid of one sheet next, which is the one down here. This one almost has a spool kind of shape. It goes up to infinity and down to minus infinity, however. It's exactly the equation for the ellipsoid, x squared over a squared plus y squared over b squared, except minus z squared over c squared equals 1. So that's the way to remember these. There's too many complicated things to memorize them rotely, but once you see the ellipsoid, it's just like the ellipse with one more term. This hyperboloid of one sheet is the ellipsoid with one minus in here. And the hyperboloid of 2 sheets, if you think about it, look at this equation here, is actually the ellipsoid with 2 minuses. If I take minus each side, it becomes minus x squared over a squared minus y squared over b squared plus z squared over c squared equals 1. The very ellipsoid equation just with minus on the first 2 terms. And it looks like this. You can see the 2 sheets. There's a surface down here and a surface up here. We can see how to sketch these actually using our techniques for conic sections. There's also some similar ones. If you just change it starts to get a little complicated because you start to deviate a little bit from that. Here's an elliptic paraboloid. The good thing is, even when you start to get more get changes in these equations, they are sort of natural. Can you see how this might be an elliptic paraboloid? The name gives it away. It means the cross sections here are ellipses and parabolas. If you look down, for instance, on this picture here, if you were to slice this vertically with a plane, you'd get this parabola down here as a cross section. If you slice it horizontally with a plane, you get this ellipse up here as a cross section. And if you slice it vertically the other way, you get a parabola that goes around this way. And so in two directions, the intersection is a parabola, and the other one is an ellipse. Hence, it's an elliptic paraboloid. And if you look at the equation, you can see it. I think once you start to understand how to draw the cross sections, and we'll do that here, then it becomes natural to remember these things. For instance, if I put y equals 0 in this equation, what I'm doing is intersecting this equation with the plane y equals 0, right? I'm taking all points that are on this elliptic paraboloid that are also on the plane y equals 0. So this term goes away, and I just have x squared over a squared minus z equals 0, right? Forget this term right here. What is that? If we were just looking in the xz plane, right? That is the y equals 0 plane. Z equals x squared over a squared is obviously a parabola, right? Z equals a constant times x squared. Similarly, if you put x equals 0, so you intersect this with the x equals 0 plane. Now you're looking in the yz plane, drop this term out, and you got z equals y squared over b squared. Again, a parabola. And so you can see by putting x equals 0 or y equals 0 that the resultant in the coordinate plane is a parabola. Finally, you put maybe z equals 1 over here. What happens if you put z equals 1 and intersect this surface in 3 space with the plane z equals 1? Well, now you've got x squared over a squared plus y squared over b squared equals 1, transferring this to the other side, putting z equals 1. That was our standard equation for an ellipse. And so if you just put those x equals 0, y equals 0, or z equals 1, you get a parabola or an ellipse. And it falls out naturally. Once you know the conic sections, you say, oh yeah, and then this is easy to memorize, I think. Here's another one. I'll go through these one at a time as much as I have time for today. The hyperbolic paraboloid. Oops. It's not a good picture up there. It's bringing back the elliptic paraboloid. The hyperbolic paraboloid is the hardest one of all, but fortunately for you, you're Oklahomans, you're used to saddles, right? It's a saddle shape. So if you think about the name, it suggests that the cross sections are hyperbolas and parabolas, and indeed they are. If you just intersect it, that's what you'll find, and you can see it. If I put, for instance, z equals 1 in here, intersecting this with the z equals 1 plane, and we'll write some of these down. Then I get x squared over a squared minus y squared over b squared equals 1, transferring the minus 1 to the other side. That was our standard equation for a hyperbola. I hope you tried the homework on those. You'd see when you put z equals 1 in this equation to intersect it with the horizontal plane z equals 1, it's just the standard equation for a hyperbola. If you put z equals any other number, that's also a hyperbola. You just have to divide through, and we'll show that shortly. So these equations come out naturally when you realize that their names suggest what they are and just try and make appropriate cross sections. Here's the other ones that we have. Let's see, I introduced all these, I guess. An elliptic cone. If you take the equation for the hyperboloid of one sheet, and instead of 1 on the right, put 0, see, it's not much difference. Change that 1 to a 0, all of a sudden it gets to be a cone. It's like an hourglass. In fact, if A equals B here, you can think about the cross sections. What you get is a circular cone, a right circular cone, we call it sometimes, because the cross sections are circles at right angles to the plane that you cut it. This becomes just an hourglass, a circular hourglass. But more generally than hourglass, this allows elliptical cross sections, as you see here. And then finally, these following here, I don't know why they put them, well, they put them here for this reason. These are degenerate quadric surfaces. In most textbooks, this elliptic cone, I always see listed as a quadric surface. You notice up here, they only list 5, and I told you there's 6. In your textbook and most textbooks, they say there's 6, and the 6th one is this elliptic cone. These other ones are considered degenerate cases, such as the elliptic cylinder. If you, in that equation I told you with ABC, all the way through J, set constants a certain way, what you can get is an ellipse extruded way. Say you slide it perpendicular to an axis and you get this elliptic cylinder. So a cylinder is gotten by just taking a plane curve and sliding it each point along parallel in the same direction. Here's, for instance, a hyperbolic cylinder. You take a hyperbola, you see it at the top, and you slide it perpendicular to the plane it's in. You get what's called a hyperbolic cylinder. You can get a parabolic cylinder. So cylinders are generated by sliding plane curves, and they are some examples of degenerate cases, and they've left out some here too. I'm kind of disappointed. For instance, a plane is a degenerate case, right? If you go back to the equation I wrote, you can put all the terms equal to zero except the constant times x, constant times y, constant times z, constant. It's a plane equation. You can see it just by looking at it. And then just as a note, a sphere is a special case of the ellipsoid, right? If you put A, B, and C all equal in that ellipsoid equation that I mentioned at the beginning, I'll write it again. What you'll see is it's your standard equations for a sphere at the origin. Again, all these equations are standard equations, just like with the conic sections. They put the center, this time of the quadric surface, at the origin in free space instead of the center of the conic section at the origin in the plane. And so this is generalizing conic sections to one more dimension is really what it's doing, getting surfaces in free space. All right, this hyperboloid of revolution, all they're saying is this is an elliptic hyperbola where you've made A and B equal in the equation so that you get circular cross sections, a special case, when the semi-axes of the ellipse are equal. And same thing here. Here's when the cross sections are circle for the hyperboloid of two sheets. So they'll list all these cases. Here's a circular cylinder when the elliptical cylinder has the two axes equal. So you can get those kind of things, and you can get no solution. All right, so that's enough for all that introduction. Let's see if I can get this back out of here. All right, so hopefully that gives a nice introduction there. And now what we want to do is some examples. I'm sorry we didn't get to do more with conic sections. I put a lecture. I have 2 classes this semester. My other lecture, I think, is out on YouTube. I'm going to start putting the recorded lectures, most of them, the ones I get recorded, out on YouTube, either from this class or the other class. And then if you miss a lecture or you want to go back and review it, you can go back and see what I did. So I did very similar stuff, but a little bit different at the end. If you want to go back and you missed this lecture on conic sections last time, that's out there. The way to find it is on Canvas, under Files. There is a file just next to a syllabus that says Calculus 3 videos or something like that. It's a PDF, and if you double click on that, it'll bring you up the addresses for the lectures that I've got put away. There are some more, but they didn't come out very well, so I didn't put them on there. Hopefully they'll come out better. I'm sorry, I've got a different laptop, so maybe this one will work better now. But you can go click on the address and it will come up, or you can paste that address into your web browser and get it. So here's an example problem. This is the kind of equation you see very frequently in applications. 3x squared minus 2y squared plus 5z squared minus 1 equals 1. And, oops, no, it's this one. There's no minus 1 here. It's just equals 1. What is that? Well, to figure out what these things are when you see them on your homework, what you should realize is they're standard equations. We consider the following that you might want to write down just for reference, even though they're all in your book. And by the way, I'm going to present these slightly differently than the book. I'll follow more Anton's approach. Anton is a classic calculus text. It's very similar to this one. I like yours better in general, but in this one, I don't like the way they did the equations. They're the same equations, just with a minus one, with minus the equation or one term on the other side kind of stuff. I find the way they put them in your book a little harder to remember. but a lot of them are the same too. So x squared over a squared plus y squared over b squared plus c squared, excuse me, z squared over c squared equals 1. This is called an ellipsoid. For a, b, and c can't be 0, you divide by 0, and then it doesn't matter, you get the same solutions whether you put a, b, c negative or positive. So it's convention just to choose a, b, and c to be any positive numbers. And then these have some very substantial meanings, which I'll show when I get to the ellipsoid. But A, B, and C turn out to be the semi-axes in 3 directions of the ellipsoid. Maybe I should just draw it just to give some flavor to this. We said it looks like this. It has elliptical cross sections. What happens is if you cut it with a plane like this, you get ellipses with semi-axes B and C. If you cut it with a plane in this direction, then you get semi-axes A and B, A and C, and then a plane in this direction, you get semi-axes A and B. And so whichever direction you cut the thing, you get an elliptical cross section, and each of the coordinate planes gives semi-axes A and B or A and C or B and C, depending on which way you cut it. And if you think about it, it's real obvious. You put z equals 0, you get this, right? So in this horizontal plane, z equals 0. If I intersect this ellipsoid with the plane z equals 0, I get the standard equation for an ellipse with semi-axis A and B. And so there it is. It's the cross section in the xy plane, z equals 0, this one, is the standard equation for the ellipse centered at the origin. So you can see immediately how to sketch this thing. Now the second one here, and by the way, your book does the same thing. They just put it like this. They put x over a quantity squared, right? Y over b quantity squared, z over c quantity squared. So it's extremely similar. I don't care which way you memorize it. I just find the other way, the first way I put it, the way that most books and, for instance, Wikipedia present it, so I prefer that. But you can put it whichever way you want, and the homework may expect it more this way. The next one is x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. Just change that 1 plus to a minus. This is a hyperboloid of one sheet. All right? Now, if you put 2 of these equal to 0, we'll put the first two, minus x squared over a squared minus y squared over b squared plus z squared over c squared equals 1. This is a hyperboloid of 2 sheets. And by the way, I mentioned before, I just want to show this. What if A, B, and C are all equal here? If A equals B equals C, then this one becomes x squared over a squared plus y squared over b squared plus z squared over c squared equals y squared over a squared plus z squared over a squared, all a squareds, equals 1. And you multiply through by a squared, you get x squared plus y squared plus z squared equals a squared. So this is 4 b equals c a. You get this equation, but this equation, x squared plus y squared plus z squared equals a squared, you remember is an equation for a sphere of radius a, right? So the ellipsoid degenerates into a sphere of radius a when a, b, and c are all equal. So I'll just make that side note. A sphere is not listed as one of the standard quadric surfaces. We have those 6 that I showed you, but as I said, some of these things like the sphere are degenerate cases of those. Not degenerate cases, but special cases. Degenerate cases are like planes and cylinders and so forth. All right. So there's the first 3 quadric surfaces. Let me get rid of this last one. I guess I better get rid of this. All right. All right, so there's 1. the ellipsoid, 2, the hyperbola of 1 sheet, 3, the hyperbola of 2 sheets. Now we got 3 more. If we take this one, a hyperbola of 1 sheet, and put the right side equals 0 instead of 1, here's what we get. We get c squared over c squared equals x squared over a squared plus y squared over b squared. That's just putting 1 on this side and reducing it. This one is called an elliptic cone because its cross sections horizontally are ellipses and it looks like an hourglass, right? With elliptic cross sections. So I'll say that's the standard equation for elliptic cone. And I started to say earlier, all these equations are standard equations. They can be rotated, and if we do that, then we get that general case, that equation with the cross terms, the xy term, yz term, and xc term. You don't see that in any of these because you have to rotate it to get those. We'll talk about plane later for rotating the conic sections, and we actually won't do these, but we'll just show how to do rotations in the plane, and then you can imagine how if you did different rotations, rotation in the xy plane, yz plane, and xc plane, you could rotate these things, you get these cross terms, x, y, y, z, z, x, and then you get those general equations for quadric surfaces. So what we're going to do for our classes, we're only going to do these things where the axes of the ellipsoid and so forth are parallel to the axes of the coordinate system, and then you have to do rotations to get more general cases, just like with the conic sections. You got the standard equations centered at the origin, the axes parallel to the coordinate axes. That's what these are also, centered at the origin, the axes parallel to the coordinate axes, but they can be rotated and you get those other general equations we mentioned. All right, so here's the elliptic cone. Then we've got this one, z equals, and by the way, on this one, I like to take this c squared out and put it like this, because really you can multiply this through by c squared and get the same set of all equations. This one is a little easier to remember, so I'll take the c squared out. I think your book puts the c squared in just to make it look like the other equation maybe. But you don't need it, you just need this. I think it's almost easier to imagine the elliptic cone this way. Because right, it's a c squared is an extra parameter multiplied through by c squared, and then you get this result. Here's another one. If I put z equals a x squared over a squared plus y squared over b squared. This is the one I mentioned before. In the y equals 0 plane, the xz plane, you get this equation. Oh, it's a parabola, right? Z equals x squared over a squared in the xz plane. If I put y equals 0 within if I put x equals 0, then within the yz coordinate plane, z equals y squared over b squared is a parabola, right? Z equals a constant times y squared, basic one from algebra. And then if you put z equals 1, for instance, you get the standard equation for an ellipse. So the cross sections are ellipses and parabolas. You get an elliptic paraboloid. Finally, if you put z equals x squared over a squared minus y squared over b squared, now if you put z equals 1, you get 1 equals all this, you get a hyperbola, right, as a cross section instead of an ellipse from this one. And if you put cross sections the other way, put y equals 0, and you get z equals x squared over a squared as a parabola up. But if you put x equals 0 within the yz coordinate plane, you get z equals minus y squared over z squared as parabolas down. And so you get parabolas up and parabolas down. And you get that shape that we showed, the saddle shape. This is the hardest one. But as you can see in the yz, in the x equals 0 plane, the yz plane of the board, you get downward parabolas. In the other direction, you get upward parabolas, and you get something that looks like this. It's a saddle that you can sit down on the origin. It's hard to draw. This is the hardest one to draw. But it's parabolas this way, up downwards. All right, here's a parabola downward here. Parabolas, that's in the YZ plane. Parabola's upward in this direction in the XZ plane. And then these are hyperbolas right here. So this is a hyperbola. This is a parabola down. And this one here on top is a parabola up. But you get that by putting one of the variables equal to 1. I'm taking a long time to do these. I have to get back to my example here. The object is to have these 6 equations and figure out which one it is. And what makes it tricky is they're not always exactly like this. What happens if I make y squared over b squared minus x squared over a squared in this one? What happens? Well, that's like interchanging the x and y axes, so it turns this saddle the other way. Now the saddle points this way and has parabolas down in this direction, come down the origin like that. There's the, oops. There's the hyperbolic paraboloid. Hope you can see that way down at the bottom. I think you can. When this term is negative and this term's positive. So you can interchange x, y, and z, and these things turn different direction. And it's still a standard equation, just with the variables interchanged. So if I put x equals z squared over a squared minus y squared over b squared, now you sit down on the saddle from the x-axis, for instance. But in the standard equation, you sit down on the saddle from the z-axis when z is by itself on the left like that. There's the 6, and now finally, it's not too long to get to an example. Sorry. Here is an equation. We want to figure out which one it is, right? Which kind of thing is this? How can we sketch it? And by the way, because it's electronic software, the homework problems are going to ask you which one is this kind of stuff, or which one could be the trace. It's kind of easy like that. On the test, which is coming up a week from Wednesday, I'm about to put the practice exam online, so look online for the practice exam Wednesday, I suppose. I'll give it to you a week ahead of time. On the test, I might ask you to actually sketch this. So be able to do the homework problems, and when you do it, be able to sketch the quadric surface, right? And then there'll also be some cylinders on there. So here's this one. Which one could this be? Well, fortunately for me, I've already got one of them, right? That looks like some of these equations. If I rewrite this equivalently as x over square root 3, x over 1 over square root 3, or x squared over 1 over square root 3 squared minus y squared over 1 over square root 2 squared plus z squared over 1 over square root 5 squared equals 1. I recognize that is a standard equation. It looks like this hyperbola in one sheet, except the minus is here instead of here, right? So you just have to rewrite these algebraically is the whole trick to the homework, to recognize one of these 6 forms. And again, I wrote them slightly different from the book, but I think this is the more natural way to do it, and pretty much the way Wikipedia did it, although it differed at least one point on that. So I recognize this is a hyperboloid of one sheet, except turned so that the hyperboloid of one sheet was a spool-like shape going around the z-axis, because this was the negative term. So this is about the y-axis because the y term is down there. And we have to erase these now, but I just wanted to show you that you look at these 6 equations and you figure out which case it is and which way it's turned. And we got something better to clean this with before my next class. All right. Here's how you can draw it accurately. Remember, it's at the origin, and we already know that the hyperboloid of one sheet was a spool, right? Where we wrote x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. We remember it looked like this. It was a spool with elliptical cross-sections this way and hyperbolic cross-sections that way. One way to do this, and what we know for here, is we're not going to get this because the y term is negative. It's going to be a spool opening about the y-axis, so it's going to look like this. If you can just draw this on the test, I'm going to give you quite a lot of credit for recognizing this. I don't expect super accurate drawings on these. People always ask me, How accurate does it need to be? I'm not going to be picky. Um, but here's how you can make it accurate. Do what we call traces. These traces are intersections with planes parallel to the axes is what we're going to do. But anyway, so traces are intersections with the planes. And we're going to choose planes parallel to the axes. And suppose I do, for instance, the x equals 0 trace. What do I get? Right? If I put x equals 0, then it becomes this. Minus y squared over 1 over square root 2 squared plus z squared over 1 over square root 5 squared equals 1. What is that? I recognize immediately from last lecture, if I've done the homework, right, that that's a hyperbola. This is the standard equation for a hyperbola within the x equals 0 plane. And so I can sketch now accurately within the YZ plane of the board, right, x comes out, a hyperbola with semi-axes, 1 over square root 5 and 1 over square root 2, right? And since the z-squared term is positive, it opens about the z-axis. So it goes up and down, just remember what I did with hyperbolas before. Here are the branches of the hyperbola. And I'll just leave it like that for the moment. There's some asymptotes that you have here that you can figure out, right? The asymptote is z equals plus or minus 1 over square root 2 over 1 over square root 5, y, which is plus or minus square root 5 halves y. So you could draw these accurately if you wanted within the x equals 0 plane of the board. I don't expect all that much accuracy. But now we can do traces in the other direction. Suppose I put instead the z equals 0 trace. Let's see. I'm sorry, the y equals 0 trace. Then I just put in the equation. This equals 0, and I've got x over 1 over square root 3 squared plus z x squared over that plus z squared over 1 over square root 5 squared equals 1. And I observe that's an ellipse, right? So these were hyperbolas because one term was negative. This is an ellipse because the standard equation for ellipse with both terms positive. And we notice the semi-axes are 1 over square root 3 and 1 over square root 5. So I can go into the y equals 0 plane with this crucial waistline, if you like, of a hyperbolate of one sheet and say that the semi-axis in the x direction is 1 over square root 3. That's this direction. So this is 1 over square root 3. And this one in the y direction is 1 over square root 5. So that's actually the key ellipse. If you can sort of sketch this cross section, I might ask you to draw it separately in the plane within the YZ or within the XZ plane, and then you can say here's the trace. Here's the y equals 0 trace. Is just this ellipse. X squared over this number squared plus z squared over this number squared equals 1 makes those the same axes. 1 over square root 3 on this axis, 1 over square root 5 on this axis, and you just say, here is the trace. And then I'll put it over here. It's this ellipse right here is the trace. Then we can do some other ones. For instance, if it's up at the top here, right? Erase the original equation. But see, this equation, when you see it, looks at that form: ax squared plus by squared plus c squared, cz squared plus etc. etc. Know immediately it's either a quadric surface or a degenerate case, or no solution. We're not going to give you no solution, right? And you can try this stuff. So now let's try the other equation. Let's try y equals 1 or something. Then this equation, actually, let's let y equal 1 over square root 2, just to make it easier. Then this term becomes 1, and I get x squared over this 1 over square root 3 squared plus z squared over 1 over square root 5 squared plus 1 over minus 1 over here equals 1 becomes equals 2. So this will become 1, and when I add it over here, I got 1 plus 1 is 2. And I'll get this equation for the y equals 1/2 trace. If y equals 1 over square root 2. So if I intersect it with this plane parallel to the yz plane, but 1 over square root 2 units over, then I can draw this ellipse here and say, oh, now the semi-axes are different, because you can divide this through by 2 and rewrite this as x squared over square root 2/3 squared plus z squared over square root 2/5 squared equals 1. That's a standard equation for an ellipse with these semi-axes. So now you can draw the semi-axis here of square root 2/5. So that's z right now. And the semi-axis in the x direction of square root 1/5. So you can see, you can sketch these traces. That's what I want you to be able to do, is just figure out a couple of traces once in a while, easy ones, like, they give you an easy equation. All right, we might have to finish some of this next time. We'll see. All right, but a lot of these second degree polynomial equations are what you're going to get, and then you have to transform them into the correct form, I guess, which one it is. I want to do one more here too. Suppose I gave you x squared minus y squared equals 1. This is a trick case because it's not any of those forms. What is it? Z is missing. If one of the variables is missing, recognize that in the xy plane, right, you can sketch this thing. Right? What is that? Think of x squared over 1 squared minus y squared over 1 squared equals 1. Oh, it's a hyperbola with a equals b equals 1. Opening about the x-axis because the x term is positive. So within the x, y plane, I have a hyperbola opening about the x-axis. There's that one, and there's this one. And it goes out to 1 and 1 because a equals 1. And then it has asymptotes, y equals plus or minus x, right? Y equals plus or minus b a x. That. And so here's the line in the xy plane, y equals x. Here's the line, y equals minus x. You can draw that hyperbola, and now z is missing. That means z is arbitrary. So now you extrude this. You slide it parallel to the z-axis, and you draw it like this. You draw the same hyperbola way up here. Just drew it in my equation. The other thing on these is to plan ahead so you have enough room. But there it is. It's a hyperbolic cylinder. When you have a variable missing, then you figure out, oh, it's a hyperbola. Oh, it's a circle. Oh, it's a whatever. And you say it's a whatever it is, cylinder. This is a hyperbola in the xy plane. When you slide it, it's called a hyperbolic cylinder. A cylinder is just gotten by sliding a plane curve along some line where all the points move parallel. Usually, for our purposes, we'll move them perpendicular to the plane of the figure. Maybe I have time for one last example. Maybe not. We'll go real quick, and we'll see if we can just kind of guess what it is about. There's just a whole bunch of homework problems I would like to do. Suppose I gave you this one. This is one of the homework problems out of web assigned. It comes up with different numbers for you probably. 2x squared plus 8y squared equals 7z. What is that? Divide it through by 7 to get a standard form. Switch sides. You got z equals 2/7 x squared plus 8/7 y squared. And the trick is just to recognize that you can convert it to one of those 6 forms. or recognize it's a cylinder if a variable is missing. Now I rewrite this as z equals x squared over square root 7/2 squared plus y squared over square root 7/8 squared. Really, should write 8 as 2 square root 2, but I'm out of time. Oh, look what that is. It's an elliptic paraboloid, right? Z equals x squared over a squared plus y squared over b squared. It's one of these things. And z is on the right by itself. It's exactly what's in the book. It's looking that I drew on the board. It's looking like this. And you can do traces similar to that last thing. If you put y equals 0, then in the xz plane, let's put x equals 0. Then in the yz plane, you've got z equals y squared over square root 7/8 squared. So that's this trace right. That's this trace right here. This trace is z equals y squared over square root 7/8 squared. And that's easy to sketch, right? It's a parabola from algebra. That's fine. You can sketch the trace in this x equals 0 plane is this. And you can do that with the other cross sections. You get this. You get ellipses in one direction, parabolas in the other. It's an elliptic paraboloid. Well, we're out of time. I'm circling over it. Sorry, I can't quite finish it. I'll pick up. I'll do a little bit more next time if you have questions, and then we'll move on to the next section. Hope you had a good morning. Nice to not have to go out in the cold. Any questions at the last second? All right. Well, thank you very much for coming in this morning, and send me emails or see me online as you have questions.
All right. Thank you.
Thank you.